Hello, my name is Francesco, and today I'm going to present my contribution for the final project. We decided to do a 3D game, which was a very exciting process, and more specifically, my contribution was along the lines of building the visual and rendering pipeline for the game's environment and some gameplay elements. I created a cube and wrote geometry from scratch using raw vertex and index data. I implemented custom color and texture mapping, optimized their visibility with dynamic shading adjustments. I set up the VAOs, the VBOs, and the EBOs, and attribute pointers to make sure that we can cleanly render through OpenGL. Now on the gameplay side, I implemented the obstacle rendering loop and the UI overlay system, which displays real-time player score and status updates directly in the game window. And yeah, these features were definitely they definitely affected the game's visual clarity and user experience. So, yes. Now I will demonstrate the project running. So as we can see in this recording, we have two screens, and we just saw both blue cars and the green car from the second screen gone. And like I will explain later, we have three lanes pretty much, which are divided with two lines, and we have obstacles moving around which eventually crash the players. And yeah. And now for part 2 of the video, I will go to the Word doc and discuss line by line but what my code does. So this is a Word doc, it's a little long. Sweet. So first over here, we create a new OpenGL buffer object, and it stores its ID in the TBO. This will be used to store the texture coordinates. Then we tell OpenGL that we want to work on the buffer we just created, and that it's an array buffer. Then here we send the actual texture coordinate data to the GPU, and this GL static draw means that data won't change frequently. Then for the next line, this tells OpenGL how to interpret the texture coordinate data. It's going to attribute index 2. Each vertex, which uses two floats, U and V, and there's no padding or offset. And then for this last line here, this enables attribute 2, the one for texture coordinates, so it'll be used for doing rendering. Then here we create a new buffer for indices. We tell OpenGL which vertices to draw and in what order. Then we bind this index buffer as the element array buffer, meaning it's now the active EBO, and then we upload the index array to the GPU. Then here we're done setting up the VAO, so we unbind it to prevent any accidental damages. Then here we check if the object color is green, which is used for player 1, and if it's player 1, we store a number of indices so we know how many to draw later. Otherwise, otherwise we just assume it's player 2 and store the index count for player 2. Then this is just a print debug message that shows how many indices were loaded for the model. And then we return the ID of the VAO we just finished setting up. Then we go here to private int. This is a method that builds a cube, and we're essentially passing red, green, and blue color components that we want to have that we want the cube to have. Then here we brighten the color a bit so it stands out more. We multiply each color by 1.5 and we clamp it to 1 max so it doesn't overflow. Then here we're starting the array of raw vertex data for the cube. Each group of 8 numbers represents 1 vertex, so 3 for position, 3 for color, and 2 for texture. Yeah, so the first 4 lines essentially define the front face of the cube, and the next 4 lines define the back face, but slightly darker by multiplying the color by 1.8. Yeah, so kind of to have that lighting effect. Then for these indices, this is a list of indices that tells OpenGL how to draw the cube using triangles. Each face of the cube has 2 triangles, meaning 6 indices. So yeah, 6 times 6 equals 36. So then here we create a VAO. By the way, VAO stands for vertex array object, and this that we create will remember all the layout and buffer bindings for this cube. Then we bind the VAO. This is kind of like saying, oh, I'm working on this cube now, something like that. Then we create a VBO, which is a vertex buffer object, to store the actual vertex data, the positions, the colors, the UVs, etc. Then we bind the VBO to the array buffer target, so you can send data to it. And then we send the big array of vertex data to the GPU. It's like saying, I don't know, it's like saying, like, here's all the info about what the cube's corners are and what color they are and how the texture should wrap, etc. Then for the so yeah, we have like attribute 0 position. We're saying that each vertex reads 3 floats starting from an offset 0, and each vertex is 8 floats apart in the array. That's kind of what it's saying. Then we turn an attribute 0. We turn on attribute 0 here, the position data, meaning the position data will now be used when drawing. Then for attribute 1, color, meaning color, this time it starts reading at the 4th float after the position, and again reads 3 floats for the RGB. And then we enable attribute 1, meaning that color data is active. And then for attribute 2, the texture coordinates, we start the 6th float in each vertex and read 2 floats. And then we turn on attribute 2, meaning that the texture UVs are ready to go. Now we create the EBO, the index buffer, that tells OpenGL the drawing order. Then we bind that EBO to the element buffer target, and then we send all those triangle drawing indices to the GPU. And yep, essentially here we're all done. So we unbind the VAO so you don't accidentally mess it up elsewhere. And we return the VAO ID. So we can use it later when rendering the cube. Well, either me or anyone in the team. And now we have this method that returns a VAO for the road, which is basically a big rectangle with some stripes. Yeah, and well, for the float vertices, it gets a little crazy over here. We're defining the vertex data for the road, so each vertex again has 8 values, 3 for position, 3 for color, 2 for texture. And then the first 4 lines, it's 10 units wide, 50 units long, and it lays flat on the y plane. Well, the y equals 0 plane, and then the color is white, meaning the textures will show up in very big brightness, full brightness. And then, well, the rest of the array just defines lane marking. So 2 vertical yellow strips on the left and right sides of the road, and then the color yellow. So yeah, it's a lot of that. Then for the indices here, I guess you consider all of this one line, which is crazy. But yeah, for the indices here, the first 6 draw the main road, the next 6 draw the left lane stripe, and the last 6 draw the right lane stripe. And then we create a new VAO to keep track of the road's buffer configuration. Then we bind the VAO, so while following buffer bindings and attribute settings apply to it. Then we create a VBO to hold the vertex data. Then we bind that VBO so we can upload data. Then we update the a vertices array to the GPU. And then we create a buffer for the indices. We bind it and we upload it to the GPU. And then finally, doing kind of the same process, attribute 0, vertex position. We enable the position attribute. For attribute 1, the color, we enable the color attribute. And for attribute 2, the texture coordinates starts like the 6th float in each vertex, and we enable here texture coordinate attribute. Then we're done with the setup and bind the VAO in order to prevent accidents or accidental changes, and then we return the VAO ID so we can bind it during rendering. And now for the last part over here, we're starting a loop to go through each obstacle in the list. Each OBS is a float array containing its X, Y, and Z position. Then we position the model matrix for this obstacle. So we're placing the cube at X, Y, Z, and we scale it slightly. Then we send the model matrix to the GPU shader. Then we bind the object to, we bind the obstacles VAO so that the OpenGL knows what geometry to draw and how. Then we draw the obstacle using 36 inches, which equals 12 triangles, meaning 6 faces of the cube. Then for this part, we turn off depth testing so that our 2D UI elements, like the score, won't get hidden behind the 3D objects. Then we switch to a no perspective projection, which is ideal for all the 2D overlays. Then we create a 4x4 matrix in memory. Then when we're filling the matrix with an identity matrix, pretty much saying like don't move or rotate anything, leave it exactly where it is drawn. Then flip just prepares the buffer for OpenGL to read. Then we send the identity matrix to the GPU as the view matrix, so there's no camera movement for the 2D UI. Then now that the 2D rendering is gone, we turn depth testing back so that any 3D rendering after this behaves normally. Then so for this part, we build a status message depending on which players are still alive. So if both are out, it's game over. If only one is out, it will say either like P1's out or P2's out, player 2. Then for this one, the final one, this updates the actual game window, the title bar, and the game name, and both players' scores as well. And and all in a dynamic status message. And yes, that would be all for my code explanations.